Hi, and welcome to Allen High School's discussion of chemical bonding at the APIBHL level. We are just beginning our unit, and we're going to be talking about the types of electrons that are involved. So we're going to start with a brief introduction before we move into the varying types of bonding. Now, we separate electrons into two categories when we talk about the atom. The inner or core, do you remember we talked about these in our periodic trends? Electrons, they're pretty content to stay where they are. We don't usually see many changes in those, certainly in the bonding situations. On the other hand, our valence electrons, our outer electrons, can sometimes be what I say a little bit fickle. They may be attracted to other atoms. So if we have two atoms here, the electrons from one atom could be attracted to the positive center of the other atom, and or vice versa. And how attractive they are in each direction is what's going to determine the bonding structure. Now, this shows an overall potential energy diagram for the bonding of, say, something like H2, hydrogen. So what we have on our different axes here, if we take a look, this axis here is our potential energy. Remember that very low potential energy tends to be stable, with attractive forces. The lower it gets, the more our attractive forces are maximized. So out here in this axis is our distance between the two atoms. Okay, and out here we have a higher potential energy because they haven't really come close enough to be attracted yet. So that potential for attraction has not been realized. Down here we have realized potential. Up here we still have all sorts of possibilities. So if you have not met your future spouse, there's all sorts of possibilities out there. There's a lot of potential for relationships. But once you are married, you've realized that potential, and hopefully it's a stable marriage. Okay, so you notice as they get closer and closer and closer together, as we move down this, they get closer and closer, the potential energy reaches this optimal place here. That distance where the potential energy is at its optimum is the bond length. And remember, that was measured in picometers. We did that in the last unit as well. So that optimal, that minimal potential energy, which is the optimal attraction, is where our bond length is to be found. Past that, you're getting the atoms so close together that it starts to quickly experience repulsion due to the two positive nuclei. Now, a few things we want to get straight here. Number one, you notice that energy decreases. Energy is released when bonds formed. Energy is required to break a bond. A bond is a force of attraction. So just like two very strong magnets, it takes energy to pull those magnets apart. That's what happens when you have a bond, a force of attraction. It takes energy to break that force of attraction. So today I was trying to think of a way to help you remember it, because for some reason it does seem to be something that students miss, is that it takes energy to break. They rhyme. So when you break, it takes energy. When you form, you free energy. Sorry, my Mimio's getting a little jumpy there. Look at all that. Isn't that easy to read? Okay, when you form, sorry, it's Saturday afternoon. When you form, you free energy. So to break, it takes; to form, you free. So maybe if you can kind of learn that, it's a little bit sing-songy, or come up with something better and share it with the rest of us. All right, so to break, it takes energy; to form, you free energy. Now, I'm going to go ahead and stop the introduction, and in our next video, we'll start talking about the different types of bonding. We add a few to pre-AP. How I'm starting this unit is, since you do have a strong pre-AP background, those of you who are at least at Allen High School with me, I'm going to start with the few that are the quickest to cover, and we'll end with the ones that take a little bit more time to cover. So until then, this is signing off.